Selecting the best isolated brick DC-DC converter for an application can pose a challenging task for the design engineer. There are a number of circumstances that can motivate a particular choice. These could be transient response, efficiency, environmental conditions, or mechanical packaging. This presentation is based on a technical article by Murata Power Solutions Field Applications Engineer Paul Knauber, and looks at some technical considerations when choosing the optimum brick converter for an application. First, we'll review the standard brick formats. Isolated brick converters are available in a range of standard formats, including 16th, 8th, quarter, half, and full brick. While this nomenclature appears to be exact fractions of the full brick, most are technically approximations only. The full brick, on which the dimensions of the other brick products are based, is 2.4 inches by 4.6 inches by 0.5 inches. Thus, a half brick is precisely 1/2 of the 4.6-inch length, while the width and height remain the same. However, the so-called quarter brick is not exactly 1/4 of the full brick standard, but is really closer to 30% of the full brick. Now, the 8th brick is also an interesting case because while the package size is again reduced from that of the quarter brick, the pin configuration of the quarter brick is maintained so that a standard 8th brick will drop into a board laid out for a standard quarter brick. Furthermore, the 8th brick is neither technically 1/8 of the full brick dimensions nor half of the quarter brick size, but is precisely 3/16 of the full brick size. Lastly, the 16th brick is really closer to 10% of the full brick standard. While these fractions are approximations of the full brick format, these formats have become widely used and accepted standard formats for isolated brick converters. The choice of a specific package is typically dictated by the power level required. Technology improvements over time mean the power levels deliverable from each have increased. The first half brick products deliver just 50 watts, while products delivering several hundred watts in the same package are available today. Board space is a key consideration in selecting a converter. Designers often want the most power in the least space. However, bearing in mind that technology will continue to lead to higher power densities, some users might be wise to select quarter brick packages whenever possible. The reason for this is that when the need for cost reduction arises later in the product life cycle, an 8th brick offering the same power may be available. This allows some flexibility for the user to drop a lower cost converter without having to alter the application printed circuit board. Isolated converters use a transformer, so there is no physical connection between the primary and secondary sides. Isolation can serve multiple purposes, including compliance with safety requirements, noise immunity, and alternate ground reference. For example, an isolated converter with a 5-volt output can be configured as plus 5 volts or minus 5 volts by simply changing which output termination is connected to the secondary ground. Isolation is particularly useful in telecom environments where the source voltage is minus 48 volts, positive ground, while most secondary voltages are configured with a negative ground. Several standards exist for isolation voltage ratings, and these sometimes require a specific class of insulation as well. Probably the most critical of these standards is EN 60601-1 covering medical equipment. There are specific equipment application types within this standard, and each have different levels of isolation required, depending upon whether or not the equipment is patient connected. The EN 60950 standard for information technology equipment requires at least 1500 volts of primary-secondary isolation. While there are exceptions to every rule, for most non-medical equipment applications, 1500 volts is adequate. Isolated brick converters are generally available with output powers ranging from approximately 50 watts up to several hundred watts. Achievable power levels for any given brick form factor remain a function of the output current and voltage, the input voltage range, the switching frequency, and the conversion efficiency. For any given output voltage, the power densities continue to increase as component technologies and optimized topologies continue to drive efficiencies higher. Many of the brick-type converters incorporate a base plate for conduction cooling or are offered with a base plate option. The base plate improves thermal performance when used in both natural convection and forced convection environments, but also allows units to be employed in conduction-cooled applications where the base plate is attached to a larger thermal sink or cold plate. Most isolated brick converters include thermal shutdown circuitry to protect the converter from damage under abnormal environmental excursions. These protective circuits result in shutdown of the converter with automatic recovery upon restoration of normal temperatures. Several degrees of hysteresis are added to avert oscillation. Input voltage ranges for brick-type converters are most typically 2 to 1, meaning that the maximum operating voltage is approximately twice the minimum. Typical examples are 18 to 36 volts and 36 to 75 volts. Murata Power Solutions also offers models with wider 4 to 1 input ranges of 9 to 36 volts and 18 to 75 volts. These 4 to 1 modules are particularly useful when system designers are confronted with environments where the available voltage can be quite disparate. A prime example of this is wireless equipment that may be powered from a nominal plus 24 volt or minus 48 volt battery system. The source voltage from the battery power systems available at the converter input can span a wide range, depending upon the state of the power system. Specifically, for a nominal 24 volt system, during periods of battery cell equalization, voltages can approach 30 volts. Conversely, if the AC power has failed and the battery cells are discharging, the available voltage can fall as low as 18 volts, when voltage drops from input isolation diodes and IR distribution drops are included. For 48 volt power systems, these figures would be doubled. So if the end-use equipment could be installed in either environment, it is easy to see that a converter input range of 18 to 60 volts could be quite useful. Now adding to that scenario the real possibility of installation where the battery plant is a nominal 60 volt system, the need to operate over a range of 18 to 75 volts quickly becomes apparent. Before the ideal brick converter for the task can be chosen, there are a number of module and application considerations that must be understood. These include understanding the load, operating environment, the effect the input voltage has on the converter efficiency ratings, trimming the output voltage, and derating. In order to perform a comprehensive analysis of the converter output requirements, several details of the load profile need to be evaluated. The first is how the load current was determined. It is all too frequent that it is calculated using worst-case power numbers from the silicon specifications, compounded with safety margins. On the other hand, an average number can be used for the calculation, which may be appropriate for thermal management, but ignore the peak demands. Another frequently employed method is to utilize requirements established with a previous generation of the product. Each of these methods have validity within limits and pitfalls when those limits are overlooked. A further question in understanding the load is whether the application presents a highly dynamic or quasi-static load profile. If the load is dynamic, then a few additional questions need to be answered, such as the particular slew rate or DIDT associated with the load changes, the load step amplitude, and the maximum voltage excursion that the load will tolerate during these excursions. The load step is from one particular load level to a lower or higher load level. Of additional importance is the duration it takes to step. This can drastically affect the bandwidth of the output impedance of the module. In cases where the load step is significant and the voltage excursion must be minimal, capacitors are frequently used to provide the short-term response while the converter handles the longer-term recovery. To this end, the effective switching frequency and the maximum load capacitance play a role in converter selection. The environment in which an isolated brick DC-DC converter will be operated is perhaps the most important parameter to be fully understood. The key elements are maximum operating temperature and airflow across the converter, which can be either natural convection or forced convection airflow from a cooling fan. When considering the application temperature, it is crucial to understand the temperature at the converter and not the ambient air temperature in which the converter is operating. In larger telecom systems that have many printed circuit boards, it is possible to see a temperature rise of 10 degrees Celsius or more between the bottom and top of a card. Therefore, it is important to understand exactly where the DC-DC converter is to be placed on the board that it is powering. Often, a converter will not see the raw ambient temperature, but some preheated temperature that is significantly higher. The biggest contributors to modeling of efficiency in the application are the input voltage at which the converter will be used and the output load. The higher the input voltage for a given DC output voltage, the less efficient the converter. The difference from a low line condition to a high line condition can be as much as 1.5%. The primary contributor to reduced efficiency at a high line condition is the switching losses of the field effect transistors or FETs on both the primary and secondary sides of the converter. The second contributor is temperature. As temperature rises, the FET RDS on goes up, which results in higher conduction losses. Typical efficiency levels for isolated DC-DC converters range from around 80% up to approximately 97.5%. This range relates mostly to the absolute output voltage, but is also influenced by the limits of the input voltage. The narrower the input range is, the more the converter operation can be optimized. Similarly, higher voltage outputs typically demonstrate lower rectification and IR losses due to the lower current levels. If output voltage margining or trimming is to be employed in the application, then this needs to be taken into account as well. If we consider a DC-DC converter with an output of 5 volts at a 10 amp load, or 50 watts of output power, then adjusting the output up by plus 10% gives 5.5 volts, and the output power increases to 55 watts. The designer needs to carefully consider whether this extra 5 watts will have an impact on the performance of the module, bearing in mind that the airflow and the ambient temperature for the application remain the same regardless of the increased power output. The same consideration applies to the use of remote sensing. The brick form factors have found the greatest adoption in telecom and datacom applications because of the wide use of forced convection cooling in these systems. For applications constrained to natural convection cooling, brick-type converters must typically be derated from their maximum capabilities, depending upon the maximum ambient air temperature. It is important to note that when selecting an isolated brick converter, the thermal derating curves should be regarded as a guideline. This is due to the fact that the tests are conducted in airflow chambers under very specific conditions, and that the realities of any application will never duplicate these conditions exactly. Due to the fact that the derating curves represent ideal operating conditions and is not necessarily representative of a final application, it is important not to use more than 90% of the derating curves for a particular converter. It is also very important to note the orientation and direction of airflow in the derating curves and if a baseplate option will be used. There are many factors affecting the selection of an isolated brick DC-DC converter for a given application. It is important to carefully consider the factors described in order to achieve the most efficient path from initial concept to a market-ready finished design. In general, for a given project, it is a good idea for the engineer to develop his design with a higher power DC-DC converter. A smaller, less powerful version can be substituted after all the testing is complete, if necessary, and without having to revisit large parts of the overall design. This training module has now ended. We hope you found it useful and relevant. For more information on products from Murata Power Solutions, please visit our website. Thanks for your time and have a great day.